I would like to warmly welcome to WPI and NEWSDR Professor Chowdhury.
So thank you all. Thank you all for coming. Thank you for inviting me and to Alex and the organization team of NEWSDR. This is a fantastic event that you guys do every year, and I'm very, very happy to be here and talk to you. So the only problem is that once Alex speaks before you, you cannot match his energy or his voice, but I will try my best. Okay. So let me start out by saying I see software-defined radio as a building block of some exciting new technologies that we are working today and what is coming ahead. So the goal of this presentation is to talk to you something about how a software-defined radio could be reused for a variety of different things, variety of different topics and research, some of which is communication, some of which is not communication. And just to give you a broader sense of it, I'm going to talk to you a little bit about the projects that we have and some of the upcoming thrusts and some of the research challenges that make this area so exciting. And to start with, I'd like to gratefully acknowledge our research sponsors, the National Science Foundation, the Office of Naval Research, the MathWorks, and the Defense Advanced Research Projects Agency, or DARPA. So thank you. You keep our lights on. You keep our gas boiler on. We get to do our research. So appreciate all the help. Now, moving on to the people who really make that happen, who make that research happen. So these are the stellar individuals. I'm very pleased and honored to be working with them. Many of them are here in this audience. And so if you have tough questions, I'll only look their side. But they are the people who have really worked on the projects that I'll be talking about ahead. We have also an alumni of WPI herself. So you know, it's a very closed and a rich collaboration environment. Now, why do I think a software-defined radio is really the game changer? It's all because I feel it is this one thing, and I'm going to just read from here because it took me most of the night to put together this verse, and then a few hours in the morning to just brush through, so I've not remembered this. So software-defined radios to manage all the spectrum bands, software-defined radios that will sense them, software-defined radios to beamform to peer radios, and in adversarial conditions jam them. Okay, so thank you. Well, I'm preparing for another vocation, I think. So, okay, so let's go a little bit deeper into what truly is a software-defined radio, the way I look at it, and where do I see it becoming even more integrated into our research. So my vision of this is based on the cognitive radio research that I have been part of for many years. Now, many trailblazers have walked this path before me, so I can't name them all. But I have been very fortunate to be at a time, at a place where this area was taking off. This was about 10 years ago or so, when there was a lot of excitement, and there still is, just to tell you that how rapidly, how fresh this area is even today. Now, the way I see this is that I look at a software-defined radio architecture as divided into multiple different functional blocks. And the way I see it is that there is an execution plane, and that's where we have the physical and the link layers. I see there's a synthesis plane. That's where we should be able to compose and create new protocols on the fly. Depending upon newer applications, new kinds of areas of deployment, newer attacks, we should be able to build these protocols from basic functional elements. So there's a synthesis step that must happen in this kind of environment. Now, if you can create such an engine that can create these blocks, the next step is really to have those blocks in which you can glue them together. You have to write those blocks. And that brings me to the functional compute blocks. And the way I see it is that there are a variety of different tools and technologies that can assist in building these tools. Many of them are open source. Many of them have generous company support. So there are multiple tools that we can use, that we can start to build them together. But think of this as the alphabet used in the language. You must know the basics to create larger sentences. And on the higher level, I look at this as two pieces of the same story. One piece builds more of the cognition, the learning, and that becomes the machine learning block you see on my right-hand side, which gives you more of an environmental awareness. You understand what is around, who is around, what kind of transmitters are around, or what should I do to understand and react. So all that would be under machine learning. And on the other side, you see there is a necessary step of optimization. And we do it all the time. We are driving a car, we are optimizing the turn of the steering wheel, the speed that we are driving at. We are analyzing multiple cars all around us, whether the cop is following me. The multiple things that I'm trying to do at the same time. Right? So this optimization, or a multi-objective optimization engine, is a must. It must give you, or you must have it to react and formulate your choice of parameters in the optimal sense. So this is the vision that I see. Now, we are taking small steps to realize this. Because if I was to give this to one of my stellar students over here and say, here, go build this, they and I will have a long career together ahead, right? But what we try to do is we try to break this down into pieces. So what I'm going to do is, in the interest of time, I'm only going to talk to you about few of the blocks and some of our learnings that we have gathered in this research, in this environment. So since machine learning is hot these days, right? And there are 3 posters outside which are dealing on just this topic. This is something that truly is different today than it was a couple of years ago. Why? Because now we can process, we can compute on huge amounts of data. So I want to tell you a little bit more about what we have been doing there, and then I'll spread over on some of the other blocks. So our main interest here in just this machine learning piece was being able to detect who a particular transmitter is. So we call this as RF fingerprinting, right? And this problem has been tackled by other researchers as well, and at different layers of the protocol stack as well. Okay? Well, we are going to do it at the sample level. So the problem here is as follows. Here you have Alice and Bob, who are known to each other, and then there is Trudy. So Trudy could announce to Bob and say that, look, I am Alice. And Bob will have to learn and figure out that this is truly not Alice, but this is someone else. So this problem can be solved, can be addressed if you come up with solid, foolproof RF fingerprinting methods. So what we're trying to do is we are trying to characterize radio hardware by purely looking at the imperfections that the transceiver chain is going to impart on the signals as the signal passes through the transmitter. Okay? So on the receiver side, you're only going to collect samples. So can you just look at the samples and then be able to interpret, yes, this is this radio, or this is not the radio that I trust? Now, there are many reasons why we want to do it that way. The first thing is we can have ways in which we can embed IDs into protocol headers, but those could be spoofed. So what if we could have a more reliable way of device authentication, which is really tied in to the electronics and the signal processing that is happening inside the software-defined radio? So device authentication, a more foolproof or a robust way for device authentication, is a need. And once we know who it is, then could we come up with better jamming techniques that is able to separate the friendlies from the adversarial radios, and then jam only that radio whom we know is not the one that we trust. So what we have done is that we started to look at what really are the causes for which there are imperfections introduced in a transmitted signal. So we started to look at the radio RF hardware itself. Now, if you try to look at the various pieces that form the transmitter chain, there is the DAC, then there should be the local oscillator, the power amplifier at the end. All of them are introducing changes or are altering your transmitted constellation point in slightly different forms. For example, if you look at the IQ imbalance on the top right, you find that the in-phase and the quadrature components of the transmitted signal are not amplified or do not have the same gain in both the different paths. And hence, there is a small shift from the ideal versus the observed in the constellation point pattern. Similarly, if you look at the local oscillator noise that is introduced, you see a small shifting because you would expect the local oscillator to produce an exact frequency of FC, but that doesn't happen. There's always going to be a small shift, FC plus some phi, which is a phase introduced that is causing the small rotation in the constellation diagram. Similarly, if you're looking at the power amplifier at the end, there is going to be a nonlinear part of operation of the power amplifier. If you're operating in that region, you're not going to have a linear shift, and hence there is going to be further distortion. So these are all ways and different signatures that are going to be introduced in the signal as it is passing through the transmitter chain. So could we identify these and understand that all these are the unique reference signatures for this particular hardware? Now, what we've done is we've collected a large amount of data. So we use the USRP X310 radios, and we connected that to a host computer. We used the wireless LAN systems toolbox from MathWorks, and we are able to generate standards compliant 5-layer frames, which we were able to transmit through. And on the receiver side, we used the B210 radio and collected them. So we have done a campaign of measurements going from about, I think, 16 X310 radios to different forms, mixing them up with the B210s, the E series, the N series, all of which we are trying to understand, could we distinguish specific hardwares? So our challenge is this. Imagine if I have 16 of these X310s, okay, 16 different X310s. I want to distinguish one of those X310s from another X310 radio using simply the received IQ samples from which I'm collecting given a standard receiver. Okay, so I'm not trying to. I could, and we have much greater accuracy when we try to distinguish between an X310 versus an N210, or even between N210s. But the question now is that these more advanced radio hardwares, could we distinguish them with high levels of accuracy? So we're just talking with some of our colleagues from National Instruments that you guys are making such good hardware, this problem is becoming more and more difficult with each passing day. So what we have done is that we have started collecting these samples, and we take a sequence, and so we have a methodical approach. We train, we validate, and we test. So just to give you a high-level view of what we are doing, we break down the IQ samples into a set of training samples, and these training samples, we group them in 128 samples. Okay? Now, these 128 samples are all in-phase and quadrature components. So they are both I and Q samples, which together form these 128 readings that we're going to input inside. We collect them over similarly over multiple of these radios. So we have N radios over here. Now, this forms a training data set. What we have done is we have extensively worked on convolutional neural network architectures, where after much investigations and wandering around in the forest of options, we've converged on an architecture like this that is seemingly giving us great results. So one of the issues that we have is how big should the convolutional layers be? How many layers should I have? What should be the sample size of the inputs? What should be the activation function that I'm going to take? All these are unknowns in this research. And to be honest with you, I don't have all the answers. What we do have is we have systematically explored a space of these various combinations, trying to understand which of these appear to work well. So this is our architecture where we are getting some great results. And what are the results? So apologize for the colors here, but for a smaller set of radios, for example, 4 radios, we are getting accuracy about nearly 100%, simply by looking at the IQ samples. As we increase this to 12 radios, it is dropping down to about 92%. Now, these are all over-the-air experiments, okay, with channel thrown in, with changes, with people walking by. So there is some noise in the system that we are capturing as well. So what you see here is a confusion matrix where you see that there's a device 0 and a device 0. So we are transmitting on device 0, and we are inferring that it must be device 0. So those are the red things along the diagonal. And the blue squares are the ones where you are transmitting on one, and you think that this is the other. Okay, so this is the blue ones are the squares which show error conditions. Just go along the diagonal for the correct detection points. So we are still developing this further. We are increasing and improving our convolutional neural network architectures further. But what we are trying to do as well is explore a very unique point. We are trying to understand that what really are you learning. For example, if you're looking at the image detection problem, if you have a cute picture of a dog playing, okay. In fact, there was this campaign where they had taken a number of cat videos on YouTube, okay, and they passed it through a convolutional neural network, trying to understand what does the neural network learn when it sees cat videos. If you look at what each of the layer learns in the middle, it looks nothing like a cat. Okay, it's an abstract integration of images, and what you see is also here. Now this is a true label. This is a cute little dog, and what you see here is that what each feature that is being learned at the intermediate layers looks nothing like what you see. So could we interpret in a wireless domain what is it that an intermediate layer is going to learn when I pass these IQ samples through it? We are trying to understand and investigate that problem, which I think is totally unknown and unsolved. So this is really the high-level open question. And if you're an interested researcher, grab onto this one, that what does the convolutional neural network learn in the wireless domain, in the intermediate layers? So with that, let me go a little bit further down into a next role or our next block of this larger vision, which is the optimization engine. Now, when I say optimization, I mean to say that the SDR does a variety of different things. It can be used for communication, but it can also be used for beamforming, for jamming, beamforming for energy transfer, and all of that in the presence of other kinds of wireless technology requires some level of optimizations to understand where should you be pointing, how would you be avoiding interference at certain locations, how would you coexist with other legacy technology. So all that is optimization. Now, I'm going to take some examples to show you more how we apply this. One of the areas of our interest is communications, energy transfer, and jamming, combining together into one cohesive picture. So think of a home environment where we have ETs, or energy transmitters. Okay, energy transmitters are deployed throughout this room, assume, and amidst this room there are various other electronic components that must be charged. So these ETs, or energy transmitters, must beam energy down to these small sensors and charge them without physical plugging in. Now for that, we need to have an action at a distance RF actuation, and that RF actuation is something that the software-defined radio is going to do. So this is an indoor vision. We also have interest in outdoors, where we are trying to charge small sensors through ambient cellular signals. Of course, there we don't use software-defined radios. We rely on existing radiation strengths in the LTE and other cellular signal bands. But for this, we are using indoor directed energy transfer using software-defined radios. Now, to give you a little bit more visualization as to what we have been doing there, we approached this problem on two different fronts. On one side, we started building energy harvesting circuits. Basically, they were rectifiers connected to a voltage multiplier, which will then store this DC energy inside a storage capacitor, which would then charge a small sensor. So that was basically what we were trying to do. But the challenges were many, because here we are operating at extremely low input power regime, something about minus 20 to minus 5 dBm. That's about what you can get. So we have gone through multiple iterations of our design going through all the way from design 1 to design 2 and to design 3. This is our latest one where we have a small Bluetooth module connected to our energy harvester, and this Bluetooth module can be run purely from LT signals outside. Now, what do we do indoors? Now, when we do indoors, we take multiple software-defined radios and we place them in an array and form a distributed set or a set of distributed transmitters for beamforming. Now, if you have a phased array which is all connected to one single SDR, the problem is simpler. I should not say simple, but simpler than distributed set of radios, each of which has a problem of phase and time synchronization issues. So here we have a number of these ETs, but now they are separate software-defined radios. And we have connected a small, in the diagram you see, in the picture you see a small power amplifier connected to the ETs, and they are choosing their phase and their frequency and their transmit power. They are exploring the space of options as they converge on the best possible choice that results in constructive signal addition at the receiver. The receiver is the energy receiver, or ER, where we have our energy harvester. Now, the problem is a little bit tricky, because as the ETs get spread around in space and there is no regular arrangement of these ETs, we can't predict exactly where they're going to be. The problem is, how do we allow their phases and their clocks to be synchronized with each other? Now, we've been exploring multiple solutions on that. The first is, let me start with this example here. The first question was, how do we ensure that the phases of the signals, assume that each ET is radiating a continuous wave signal. How do we ensure that these phases of these signals arrive with constructive addition at the target receiver? Now, to do that, we allow each ET to make a small adjustment in its phase. Okay? Now, assume that the frequency is uniform and set, but we're only trying to adjust the phase. Now, for that, we run, I'll show you the algorithm later on. We use a 1-bit feedback that is given by the receiver, saying that, look, in the last configuration, I received more energy. Now, that's all that the receiver is going to give you. Now, the ETs would have to just take that feedback and decide in a distributed manner what they must do. Should they change the phase of their own phase a little on the positive direction, on the negative direction, or just stay as they are? And this problem is a little bit more difficult when the number of ETs scales up quickly. So 2 ETs, easy. 3, 4, 5 ETs, very hard to converge. So this convergence is a problem that we have tried to tackle. We use a variety of techniques. One of the techniques that are possible are it trades off between exploration versus exploitation. It decides whether you will choose to explore a small change in your phase, or whether you will exploit the change that you already have and what you enjoy currently. So there are a number of these, a family of algorithms on this. We call them as the bandit algorithms. They choose between trying out something new versus staying and exploring what you have currently, and it takes a while to converge. So what we are doing now is we are pushing this forward into other ways of estimating the channel state, and even blind channel state. And could we do all what we have done and use less information from the receiver? So what you see on the right-hand side simply tells you that as I increase the number of ETs, the amount of received energy increases exponentially, and which is what we expect. This is what the theory gives you. It's not a linear increase. There's a more than a linear increase because of the way in which the signal constructions happen. Now, what if we take this problem a little bit further? Now, in this previous example, I showed you a couple of software-defined radios placed in a planar array. What if now I take that planar array, okay, and I make it vertical? Okay, so now I have a vertical array of software-defined radios, and these radios could have, or there could be many of them. Think of them as, or think of this as a building block towards a massive MIMO composed of individual software-defined radios. So here I have a plane of SDR transmitters. Now, can I take these antennas of these SDR transmitters and assume and just make them point sources on this plane, which is what you see in the second diagram over there. Now, the question or the problem that I'm given is as follows. I have so many users that are spread out in a geographical area. Each user has a different required throughput, different distance from this plane. And now all I have to do is I have to decide which set of radios, or in other words, which set of these transmitter antennas must be grouped together to form a distributed beamforming pattern. Okay. And this beamforming pattern should be done in such a way that as you can see in the third image over there, each such beamforming pattern is able to hit that particular user and give that user the required data rate that the user needs. And we must be able to do this while mitigating interference to other users who do not wish to be interrupted. Okay. So this is a logical step forward. And the problem that again happens is the time and frequency synchronization here. Now, if I'm able to connect them using a single external clock, this problem is simpler. Now, what we have tried to do in our lab is we are exploring with a technique called as the air clock, where we are trying to transmit two tones spread out or separated by 10 megahertz exactly. And these are sent over the air, and these serve as reference inputs or reference clock inputs to the SDR array, where given the two tones, if I take these two sine components, say sine of f1, 2 pi f1 c ct, and then 2 pi f c2t, and if I combine them, if I add these two sine components, okay, and then I multiply these two additions of these sines, I get a component which is a sine product. Okay. Any sine product can be broken down into a plus b, a minus b. If I have sine a into sine b, I can break them down into sine a plus b, sine a minus b. I can break them down into these two components. That a plus b, a minus b, that difference is able to generate the 10 megahertz clock, while I just throw out one of the frequency components and keep one. So that is something that we are trying to do, and trying to keep a rigid time synchronization across the SDR plane. Now, we are still in the early days of that, but the goal is that we have done some simulations based on what we can do with this SDR array. Now, simulations are quite promising, and we have again used the tools from MathWorks to work on this. We have used a variety of different optimization techniques which allocate antennas to particular users. Now, one of the cool things here is as follows. The work so far has looked at regular grouping of software-defined radios. For example, here is a grid, or here is a square of these 4 radios. Go and do beamform to that user. What we are trying to do is create arbitrary patterns of these radios. So here there is one, here there's a second, here there's a third. And because these are what you got. These are either the resources that remain, or these are because of location issues, and so these are the parameters that have been given to you. So given also that we are allowed to use software-defined radios that are not in a rigid grid pattern to form beams, how good a beam can be formed? That's also a component of this optimization. So what you see here is, just to give you a quick look of what we are, where we are, look at all the deep blue squares on the top left diagram. Now, all those deep blue squares are the software-defined radios that are going to work together for forming a beam to a particular user, let's say user 1. All the green squares are going to work together. These are the individual software-defined radios. They're going to work together to form a beam towards a different user, user 4. So given this kind of a pattern, this is by the way, a result of the optimization, how good or what can we do to satisfy a large number of requests? And so we have gotten fairly good results, and this is just to give you a sense of where we are. If you look at the bottom row, we have a user 1 which is getting really high directivity because of the deep blue SDRs that have been grouped together, while the same group offers very low interference to the other SDRs, which you can see in the other beam pattern visualization plots on the right-hand side. So we can achieve really targeted directional beams using arbitrary locations of the software-defined radios. And to us, that's a more practical environment in which software-defined radios could be used to generate massive MIMO or larger kinds of beam patterns. So, this is still an ongoing work. We will have further results in the next few weeks, but this is something that I wanted to share. Of course, we are seeing already that even at this early stage, we are getting much better capacity with, or as we relax this the geometric restriction. If we can pick SDRs across the plane, we get much better performance than simply grouping them in localized manners. So we will look at this further. We will investigate this further, and especially find out these bounds in which the performance falls when the SDRs get too separated. So we are looking at this from a both theoretical as well as from a implementation, a simulation point of view, and this is something that this is an area we are very interested in. What if we take this planar array and we disrupt this, and we say now we can have it in 3D? What would change then? So we've been looking at some additional scenarios where we take these software-defined radios and now we change their height with respect to a given receiver. And we try to see what would be the, as you can see here, here's the receiver, and here are the USRP radios at different heights. And we are trying to do the same beamforming, but now the antennas are not exactly in the same planar height with respect to each other. Because as the heights change, as you can see, as the heights change between 0, 45 to 90, clearly there is going to be a big difference in the received energy as well. So the signal strength varies. Now the question that we ask is, in a real practical environment, we can never assume that these antennas are going to be exactly at the same plane. There is going to be some angular difference. Can we factor these as well into our optimization? That is a next step that we are using some, or based on some of our initial investigations on how the antennas, the angle of the antennas affects the quality of the beamforming result. So what is the natural next step with this? Here we have a planar array. So we started out with distributed software-defined radios and beamforming on a plane. We took it and we raised it to an arbitrary distribution of the software-defined radios in the plane. We then took it and we raised it to multiple heights or differential heights. Now there's only one way forward, right? The only way forward is the sky is the limit. So could we take these software-defined radios, put them on the UAVs, and form a distributed aerial beamforming system? And what would be the challenges and the real-time adjustments that we would need to do to counter for the continuous hovering motion of these flying devices? So this is an area that we have some early results on as well. What we try to do is we have these UAVs forming a mesh network with each other. We use the Batman protocol. It's based on the 802.11n. They exchange information with each other about where their location is and other location information. And we are being able to replicate the same beamforming algorithm on these flying UAVs as well. Now we are getting good results, starting with good results. We were hoping to have a slightly higher received power, but that's because we are not fully optimizing we are not fully adjusting for the hovering motions. So this is a very interesting closed loop optimization problem. An action of the UAV must be factored into the comm system design. So this is something that I think will be very exciting in the days ahead. Now, what I'm going to do is I'm going to move through at a very high level some of the open challenges that we struggle with today. And one of them is an awareness that computation is as important as communication today, when we are talking about software-defined radio work. So if you are looking at, if you're a wireless engineer, if you are trying to get into this area, we must have that background in computation. So we did a lot of work previously on using, we use a lot of MathWorks tools where we try to understand, could we create different flows in which we could create a special executable for the ARM. We use the MATLAB Coder to create the C code, which then loads down onto the ARM executable, which runs on board on the FPGA. And the other side we could do is, the ARM, which runs on the ARM processor. The other thing we could do is we could generate HDL code, use the Xilinx Vivado tools to generate the FPGA bit stream, and run it on the FPGA on board the software-defined radio. So here you have the ARM processor, you have the FPGA, and you also have the host machine sitting at the back end. So which computing element are you going to distribute to which of these compute resources? Now that is an important problem that we need to solve, irrespective of what application we are going to look at. So this is something that we've been ourselves researching, but this area is fairly open. We've been looking at ways in which we can speed up computation by looking at tools such as MATLAB Coder and the MEX files. Just to give you a sense, we implemented an 82.11 5MAC protocol on ETS N210 radios, and the code is available from the MathWorks Central website. It's also available on my website. So we have released this code for all to use. Now, what we see is that we can speed up the processing if we use certain tricks and tools that are supported, that are given to you by, for example, the MATLAB Coder. And you can see two things. You can see the dark bars give you that you can execute faster. Now, what is the RFFE? It's a bunch of these different processing components that you see on the left. Radio frequency front end, which includes gain control, coarse frequency offset compensation, raised cosine filter, and so on. Not only will some of these tools execute faster, but also there is less variation in time. Okay? And that is sometimes very critical for software-defined radio design. If you know for certain that there is going to be some variance in your time, in your execution time, you can adjust for it. And because of this, as you can see, if you see the dark bar, especially at the frequency resolution of 100 hertz, you find that the variance is very small. And that is something that we really need to write good code for software-defined radios. We are also looking at mixed modes of computation. We have one project where we have intra-body communications, and we are using software-defined radios for that. So, of course, we don't put this radio inside the body. We have a tissue sample, an artificial tissue sample, and we are injecting signals through these tissue samples. So what would we do if you could have a reverse channel at the back end where we could take the signal back and have a much faster feedback loop? So we're looking at this mixed mode computation as well. Just to give you a sense of other areas that we are very interested in, we are looking at also open source tools like RFNOC. We are trying to see what blocks could be injected inside an FPGA, whether it is easy for us as wireless engineers to build these kinds of tools. We are working with our colleagues at National Instruments and seeing if we can define these blocks in a way that it becomes easy for future experimenters to play with them. So these are some of the areas where we can perform faster computation, faster beamforming, if we can do some onboard FPGA work. I'm going to take 2 minutes more and very quickly run through one last piece, which is also important. Important because where do I see the wireless research going forward? I see wireless research going outside of our little labs and our individual radios onto city scale, community scale experimentation. And we are very fortunate to be part of this. We call this as the Platforms for Advanced Wireless Research. I am part of the Power Project Office. And so this project office, this is mainly designed to quickly accelerate deployment in real-world test cases. So what are we trying to do? I don't know if let's say something interesting.
The Valley of Death.
The Valley of Death, yes. So for those of us, my colleagues in the industry, have seen this many times before. where we start off with something from the university, and by the time it becomes taken by a major firm or corporation, there is a time in which there is not much happening. We want to quickly bridge that gap. Now, what is this project about? So this is the Power Project Office is administering $100 million of funding and an in-kind contribution generously given by the National Science Foundation and an industry consortium. And together, the consortium and the NSF wants to see really forward-thinking wireless technologies being deployed. And I'll just quickly mention to you 2 awards that just happened a few weeks ago. Cosmos, which is going to create a cloud-enhanced, open software-defined mobile wireless testbed, and they are going to deploy this in Manhattan, where they will have millimeter wave communication, optical switching technology, all this in a real environment. And you'll be able to log in and run your experiments on this platform once it is ready. Their second platform is going to be based in Utah and will be supported by a massive MIMO base station supplied by Rice University. And that also will be completely, you will be able to program them, you'll be able to work on them. And these are just 2 of the awarded projects. 2 more are going to come. And I just want to thank a lot of our sponsors and industry contributors and sponsors for this. We already have a number of industry sponsors in this room itself. And for fear that I may miss someone out, I'll not name all of them. But here's a shout out to all of you guys who are part of Power. Thank you for this. In conclusion, I just want to say a few things. Intelligent radios will continue to evolve. We need to emphasize on this, integrate, embrace learning. Software-defined radio should go beyond communication. There's going to be actuation, sensing, jamming, energy transfer. Think of the world, and we can do it with this. And computation. We must be able to work and embrace computation and tools of computation within our design flows. And finally, one last thing. And Alex, you brought this upon yourself, inviting me on the 4th of May. May the 4th be with you. Thank you.